head first. All right. So all of these problems here kind of relate to the same idea. And I've just kind of addressed number 6 and 7 for you. So I'm going to skip those. I'll put stars on them and go right to number 8. You can cross off number 9 because they eliminated hyperbolic functions from the curriculum, so we don't have to worry about it. But the thing is, I leave it there because eventually they're going to turn around and put it back in, and I want to have my example ready to rock and roll. So, but for number 8, we have coefficients a and b in front of the trig function. So again, I know that cosine squared theta, but I'm going to use a, plus sine squared a is equal to 1. That I know. So what I'm going to do is I'm going to manipulate these so that they're solved for cosine and sine respectively. All right, so in the case of the first equation, all I'm doing is dividing out an a. So cosine of t is equal to x over a. All right, and sine of t is equal to y over b. I think this is like the math lover's problem. If you like math, if you love math, then when you see the outcome for this, you can be like, wow, that's pretty cool. All right. So cosine squared, I'm just going to write parentheses squared, plus sine squared, same deal. I'm replacing the cosine, I'll go purple, with an x over a. And the sine is going to get replaced with a y over b. Now, I know I said before that you don't simplify unless you're told to, but this is one of those cases where I can't resist. So x squared over a squared plus y squared over b squared is equal to 1. Now, this is the moment of truth. Does anybody know what type of equation that is? Ellipse, exactamundo. So we just learned in parametric form the general model for the equation of an ellipse. That's pretty awesome. And, you know, if we knew about hyperbolic trig functions, you know, because they used to be in the Calc 2 curriculum, and so we build off of it in here, but it's gone. But this one would end up giving you the equation of a hyperbola, right? So same equation but with a minus sign in between, right? So if you remember conic sections from pre-calc, you probably remember them being kind of detailed. That's the nice way of putting it. A lot of tiny steps. You know, like you create the graph, but then you have to find all the coordinates, things like that. I would just ask you, if you had a choice, even just forgetting about the unit conic sections, you have a graphing calculator and the fighting spirit. Okay? If I tell you you have a choice, you can graph this equation in rectangular form or this set of equations in parametric form, what do you choose? Every day of the week, twice on Sunday. Yeah, this one you have to solve for y in terms of x, and don't forget the plus or minus when you take the square root. So you're already not interested in doing that. Here, you're looking at two equations that are barely more complicated than a linear equation in terms of what you have to type into a calculator, right? But both of them are going to give you the equation, the graph of an ellipse. Also, just something to bear in mind. If you've ever tried in function mode, if you've ever tried graphing anything that's circular, you know, so anything that would fail the vertical line test, really, it doesn't do such a hot job of matching up the pieces. So like we would have to solve this for y in terms of x. We'd get the plus or minus. Then we have to put the equation in as two separate equations. And then the top half of the ellipse would merge theoretically with the bottom half of the ellipse, but it always leaves like a little gap. Like you just have to kind of believe that it's connected and it's fine. You get over it very quickly. But in polar form and parametric form, the calculator has no trouble whatsoever doing circular graphs.
Is that why the calculator didn't show the bottom half of the example?
Correct. All right. So number 10, converting into parametric form. Right? We explored plenty getting it into rectangular form, but going into parametric form is a little bit different. So that being said, I think it's a lot easier. So it's not like we're building up in difficulty. So they tell us to let t equal x. All right, so now I know x is equal to t. Cool. So I could do my substitution because I'm just replacing x with t. Y equals t squared plus 2t. All right, so for my parametric equations, your calculator represents the notation somewhat different from the way that we do. Not crazy different, but I think it's different actually. Let me just look. Yeah, it uses subscripts. We're going to represent our parametrics using function notation. So we're going to say x of t and y of t. And despite what the calculator does, and this is the annoying part, we're using the parameter t as a lowercase t, right? Not the capital T, right? I think I explained why the calculator uses capitals more than lowercase is because of the pixels, the rectangular pixels, so that's where it's at. All right, x of t is equal to t. And that was given right here. And then y of t would be equal to t squared plus 2t. All right. In the second case, if I cross multiply, I get x equals 2t. And then I can pop that in. Y equals meh squared plus 2 times meh. And again, just take note of whether a question asks you to simplify or not. Doesn't say and simplify, then there's no need to, but I'm going to do it. So 4t squared plus 4t. And so just to get it in the appropriate form, we're going to rewrite x of t is equal to 2t, y of t is equal to 4t squared plus 4t. Now, a legitimate question would be something along the lines of, all right, cool, makes sense. What if you're not given the let statements? What if they don't tell you let t equal this, t equal that? The answer to that is, well, you can't do anything. If you haven't defined your parameter, you can't actually convert into parametric form. So you need to know what the relationship is between t and one of the two variables, right, in order to convert into parametric form. So in like a real life setting, parametrics are defined based off of data analysis, all right? So you would analyze the relationship maybe using a regression, linear regression or quadratic regression or something like that, the relationship between t and either x or y based on data collected over a period of time, and then that becomes your parametric substitution, all right? So what does that mean for us? It means I got to tell you what the let statement is, otherwise I'll have like, what do we got, 11 people in here now? 11 different versions of a solution to this problem on a test. So I'll have to say let t equal this, that, or the other thing. All right. So in the next one, x would be equal to t minus 1. So same deal. Oh, forgot my equal sign. Now for the other problems, when I was saying don't bother simplifying unless you're asked to, it was kind of like, yeah, well, there wasn't really much to simplify, so I'm just going to do it. Here, now, I really don't want to do it. I don't want to distribute this out. Right?
So in this, like, in an example like this, we don't have to.
Correct.
Leave it like that.
Yeah, that's what I would do. So x of t, just to have the proper notation, t minus 1, y of t, t minus 1 squared plus 2 times t minus 1. And like, I mean, I look at everything through a teacher lens. So I am looking at this as saying, well, instructionally, this is a better way of referencing the quadratic that comes out in your y equation, because that shows a translation, right? This would be a case where if you had an ordinary graph, t squared plus 2t, like if you knew what that graph looked like, that's great. This is just shifted 1 unit, every point shifted 1 unit to the right. So this is actually a more beneficial way of representing your equation than to actually distribute it out and get it into ax squared plus bx plus c form. Right? But that's just the way my brain works from like 20 plus years of experience. So if you don't think like that, that's not a knock on you. It's just I've been doing it longer, so I better be thinking on a higher level.
It's so confusing. You said initially x is equal to t minus 1, and then you go down again and say x of t is equal to t minus 1. What's the difference with it?
Oh, I was just rewriting it in the proper notation.
Oh.
Yeah, that's all.
So if you wanted us to simplify, would you say let t of x plus 1, and then next we write to simplify more, or how would you represent when you wanted us to simplify it?
And simplify.
Okay.
Yeah, it'll be very clear. I generally use italics on the simplify also, so it stands out. Yeah, it's really strange to think that like the world of trigonometry that you learned about, unit circle based trigonometry, is only just scratching the surface of it, because then you got the hyperbolic trig, and that opens up a different can of worms. But here we're just talking about eliminating the parameter, right? So I kind of stole my own thunder a little bit by going right to number 8, because that was like a little bit of a spoiler, but that's all right. It's still very satisfying when you get these problems. So the first move is recognizing that there is an identity that could be used in this circumstance, and that is that cosine squared theta plus sine squared theta is equal to 1. All right, and then just off on the side, you can make a note that cosine theta, because I'm just dividing both sides by 3, cosine theta is equal to x over 3. Sine of theta is equal to y over 4. So then it's just direct substitution. X over 3 quantity squared plus y over 4 also squared is equal to 1. And then I mentioned this a few times last class, and that is, if the directions don't tell you to simplify, you don't have to simplify on a test. I just have the tendency to want to do it in class. Okay. Now, this is one of those tricky situations or weird situations where it's actually, I would think, easier to graph it by hand in rectangular form, so XY form. Sorry, this is going to be a thing all night. But it's easier to graph it in the calculator in well, this is an extension of polar form, parametric form. So you kind of, you're exposed to all the different tools and avenues to evaluate functions, but really it's up to you to decide what approach makes sense in any particular circumstance. Like, for example, if a question asked me to find the derivative, dy dx, I would prefer to use the parametric approach with the original functions, much easier than finding the derivative even implicitly with the x squared over 9 plus y squared over 16 equals 1. All right? So, but one way or the other, if you come up with the derivative, you've done it. You've accomplished the goal, so, who's to say what way is better? All right? I mean, aside from me, but, in a vacuum, who's to say what's better? Now, just to give you a little bit of a refresher, because pre-calc was a long time ago. Oh, and fun fact, in some cases, it never happened. I only learned that recently, that some school districts eliminated their pre-calc programs. I had no idea. They just jumped right from Algebra 2 to Calculus. Now, my school district has what they call a GAP program. It's a condensed 3 courses in 2 years program. But some schools just say you're going to do algebra, geometry, Algebra 2 / trig, and then you're jumping right to calculus. So it is conceivable, however unlikely, that you may have made it all the way through without ever learning how to graph an ellipse. All right. So I'm just going to give you the quickest of crash courses on it. All right. So this is the equation of ellipse with the center at 0, 0. And actually, just to kind of clarify, if you go right down to what we did for number 8, this is the standard form for the ellipse whose center is at 0, 0. All right. There are ways to handle ellipses whose center is not at 0, 0, but the best way to handle those would be to plot it at 0, 0, then translate all the points. All right, or at least that's the most straightforward way. Maybe it's not the best way. Say it again. What's that? Say one more. Oh, totally, yeah.
So like, isn't it like to the right? It's like on the x-axis. It goes away. It goes like up to 3 and then -3, and then the y goes up to 4 and then -4.
You got it. Yeah, that's a good spoiler. That's not they all died at the end spoiler. Like Mark Ruffalo. Honestly, I thought it was a big joke when he came out with that spoiler. When he was sitting there with Don Cheadle. And he said, like, everybody dies at the end. And then Don Cheadle was like, dude! I just thought he was kidding. And then they all dusted away. It's like, whoa. Okay, maybe they all didn't go, but you're pretty spot on. By the way, if you haven't seen Infinity War, like, I'm spoiling that. I don't care. I mean, it's a year and a half, I'm debating whether I'm going to spoil Endgame for you. Nah, I'll let that go. I'll still talk in code.
Infinity War was better than Endgame.
I thought so too. Yeah, I thought in all the ways. Yeah, so story wise, in terms of the visuals, the one nod I would give to Endgame, I think I give the music to Endgame. So that's the thing there, because I mean I watched the movie like 15 times, and then I've listened to the score repeatedly, and I'll tell you right now, nothing gets you pumped up like that Portals track on the score. Yeah, you get fired up. I don't even know what Avengers Assemble means.
You listen to it in the car right to school?
Oh yeah, like getting ready to go, like bursting out of the door. I'm like, ready to teach now, everybody. Nah, it's not that bad, but it's right there.
Endgame just seemed weird to me. Like the acting.
That, and also, I think it was the complete change in tone of the Thanos character.
Yeah, that was weird.
Like, just because it was a bunch of years, or his version of it was early.
They just chopped his head off like in the beginning or
Yeah, it was like, listen, this isn't your father's Avengers movie, you know, like we're gonna get down and dirty right now, you know. I think that's what they were going for, but I don't know. Yeah, but I mean, I felt like I was punched in the gut walking out of Infinity War. Like the whole theater was silent. Everybody walked out with their heads down. Yeah.
And the one opportunity they really missed out on was the Hulk versus Thanos. Because like in the movie before, he had his ass whooped, and like you would expect them to have a rematch, you know.
They never paid it off.
Yeah, right?
Yeah. Yeah, I would have liked to see that too.
I'm not a big fan of the Captain Marvel character.
Yeah,
Right? Yeah. You ever see it in interviews?
Well, you know, the thing is, I liked the movie Captain Marvel, but then the way she was used in Endgame, I thought could have been a little bit better. Because the first thing they said was like, well, we're not going to use her as like the person to solve all the problems at the end. And then there she comes flying through space, like, takes down the ship, and it's like, well, you kind of did use her to solve all the problems, so. It's out on Blu-ray if anybody hasn't seen it and needs to see it now. I respect that. So some might be wondering where the 3 and the 4 came from. The 3 is the square root of this bad boy. And the 4 is the square root of that one. All right, because the square root of 9 is associated with the x term. X is the horizontal movement. That tells us that our deviation from center is 3. And because the square root of 16, which is 4, is associated with the y, that's a vertical movement, and so that's why our deviation there is 4. All right, so, I mean, I'm definitely not doing the topic justice, but it's kind of important that you're able to come up with some reasonable visuals of conic sections, or at least ellipses and circles to start. So that's kind of where I need you to be. The good news is we don't really have to worry about the center not being at the origin, right? And when we get to more complicated situations and get into 3D, you'll see why that's the case. All right, so for now, I just ask you to trust me on it, and later there'll be a payoff. For number 7, we're looking at, again, an identity, and that identity is cosine squared of A, quote unquote A, in this case 2 theta, plus sine squared of that same A is equal to 1. And so we know that x and cosine of 2 theta are the same thing, so we have x squared plus y squared equals 1. All right. The only thing that allows this to be different from any other unit circle, because we talked about this last time, is the frequency. All right, so same path, just varying numbers of times that you're traveling around that path, right? In a certain period, right? And with that in mind, we can develop speed equations, angular motion, and all that stuff. So, so more on that later. So given the parametric equations, find dy dx, so first and second derivative. All right, so what I'm going to do first is just off on the side, I'm going to jot down the x equation in its most convenient form. And I'm also going to do the same thing for the y equation. But the y equation is already in its convenient form. Most convenient is power rule ready. All right, so if it's in the form that's ready to apply the power rule, then you're in good shape. I know some folks like to go with the prime notation for derivatives. I would caution against that because we're going to be taking derivatives with respect to a variety of different variables. It's very easy to lose track of what you're differentiating with respect to. So the dx, dt, dy, dt, that notation is a better way to go. All right. So the first derivative of 2t to the 1/2 would be what? T to the negative 1/2. All right, and what about 3t squared minus 2t? 6t minus 2. Exactly. So I just need dy dx, which is dy dt over dx dt. So 6t minus 2 over t to the negative 1/2. Now, it's up to you at this point if you want to leave it in this form, but I say the same thing in my Calc 1 and 2 classes where I tell them you don't have to simplify unless I tell you. But in some cases, it's in your best interest to simplify even if I don't tell you. You got to take the second derivative. You want to take the second derivative of this, or do you want to take the second derivative of something that's simpler? I think we all know the answer to that. All right, so I'm going to clean it up a little bit. So the negative power can bring that t up to the top. So t to the 1/2 times 6t minus 2. And then I'm just going to run it through. Distribute it. 6, that's not a 6. Crazy. 6t to the 3/2. Keep the base out of the exponents. Minus 2t to the 1/2 power. Power rule ready. It's the name of the game. So my second derivative, I want to take the derivative of what I just got. So notation-wise, ddt of dy dt over dx dt. Get that whole answer and divide it by dx dt. So the derivative with respect to t, I'm going a little heavy with the notation. You wouldn't necessarily write all this. You can skip around stepwise. I'm just doing it for note-taking purposes. So 6t to the 3/2 minus 2t to the 1/2. That's what I'll be differentiating. But on the bottom, dx dt, I already know that. All right, that's t to the negative 1/2 power. All right, so whereas before with the first derivative, it was in my best interest to simplify. Once I get the derivative of the top, I don't need to simplify, all right? Because there's no value in doing that, all right? So power rule. What's 6t to the 3/2 going to become? What do we say? 9t to the 1/2, yeah. Then minus, the bottom is going to stay put. Negative 2t to the 1/2 becomes? To the negative 1/2. Clean that up a little bit. And like I said, it's up to you if you want to go further with it. It actually kind of cleans up pretty nicely if you go further. Because it would be the same as saying t to the 1/2 times 9t to the 1/2 minus t to the negative 1/2, and then run it through. Keep the base, add the exponents, you get 9t minus 1. So a lot nicer than you would probably expect. And that tends to happen. You know, you got some problems that look like maybe a monstrous mess, but they end up becoming all right in the end. All right, you got to see it through. All right. So that's the skill associated with it. So it's not terrible. Just takes a little time. I'm going to put a star on numbers 2 and 3 because these are the kind of problems that I want you to experience before I go over them. I don't want to just take you through them right now because if I did, then I'd be removing all the thinking on your end. And so that's not a good thing, right? So like, I want you to experience these problems. Succeed, fail, it doesn't matter, we'll go over them together, all right? But try them first before I go over them. So let's go back a page and talk about arc length. But so that would be page 6. Numbers 2 and 3 are the next arc problems. Given the parametric equations x equals 4 cosine t and y equals 3 sine t, write an equation of the tangent line to the curve at the point where t is equal to 3 pi over 4. All right, so equation of a tangent line, that should sound Calc 1 familiar. So we need our derivative, we need the slope of the tangent line, so I need dy dx. So I'm going to need dy dt over dx dt. So just over on the side here, I could just chuck that in there, dx dt and dy dt. All right, derivative of cosine is what? Negative sine. So in this case, negative 4 sine t. This is with respect to t, so we're in good shape. We don't have to worry about anything like implicit differentiation or anything like that. Derivative of sine is cosine. So 3 cosine of t. Okay, so a ratio of 3 cosine t to negative 4 sine of t. This is where knowledge of the unit circle would come into play, because if I'm going to find the equation of a tangent line when t is equal to 3 pi over 4, I need a few ingredients. The first ingredient after the derivative would be the derivative evaluated, dy dx, when t is equal to 3 pi over 4. All right, now we can convert, if we wanted to, cosine over sine is the same as cotangent, but you know, going around the unit circle, I have faith that most people know their cosines and sines, somewhat less faith that they know their tangents, and even less faith that they know their secants, cosecants, and cotangents. All right, so if you keep it in terms of sines and cosines, it's going to be your best bet. All right, so we're looking at 3 cosine of 3 pi over 4, and then negative 4 sine of 3 pi over 4. And I'm just thinking of that as a general rule of thumb. In this case, because it's a 45-degree reference angle, if it's cotangent or tangent, it's going to be some kind of 1, either positive or negative. So you could kind of wiggle your way around it, but I want to show you this way so that you're prepared for all possible cases. All right, so 3 times meh, and negative 4 times an additional meh. All right, does anybody know what the cosine of 3 pi over 4 is? It would. It sure is. Very good. And what about the sine of 3 pi over 4?
Same.
Same but positive. All right, we're looking at a second quadrant measure. So cosine would be negative, sine would be positive. And it's one of those things where, and I'll just draw out a quick sketch of it, just because it's going to be a recurring theme in the course. 3 pi over 4 puts you about right here, ballpark. So based off of ASTC, we know that only the sine function is going to be positive there, or the reciprocal. Cosine, tangent, and the reciprocals of those would be negative. All right, so that's my indicator that I'm looking at a negative for cosine and a positive for sine. All right, but this movement is also going to be important because one of the big components of this course, or at least the part that makes it the most challenging, is the spatial reasoning. So I know that I have this ongoing battle with folks that teach at my high school of how they teach unit circle trig. And I look at it like, well, it's called unit circle trig, so there better be a circle involved. And some of them just say, okay, I just want them to know the facts. Right? So the students can regurgitate the information, and that's good enough for solving equations. But then when you get into a class like this, and you actually need to know where on a surface a particular angle is going to fall, that changes things. Right? So the rote memorization ends up being okay, whereas the actual understanding of where an angle falls on a circle is even more important. And so what I do is I offer for the first unit a bonus opportunity. I'll send it out tonight. It's an online, it's a little game, it's a unit circle game. Not only does it ask you to determine particular values, but it also requires that you place it appropriately on the circle, right? So it might say the cosine of, I'll say pi over 6, and then that cosine of pi over 6, you know that that's going to be the 30-degree angle, so you know that's going to be radical 3 over 2, but you have to place it in the appropriate location. All right. So I'll address all the rules of the bonus and how you can get the bonus credit and all that stuff later, but that's how important it is to me that I'm willing to offer bonus for you to even practice it. All right. And even in this stage of the game. All right. Well, anyway, enough of that. If we simplify, these would cancel, the negatives would become positive, and we would just end up with 3/4. All right, so that's the slope of the tangent line when t is equal to 3 pi over 4. All right, and we know just based off the fact that we've evaluated situations like this, we convert it to rectangular form, that we're looking at an ellipse. And so if that's the case, on that ellipse, there's going to be multiple situations where you're going to have zero slope and undefined slopes, and then there's going to be cases where you have that slope of 3/4, so a positive slope. But it could happen in more than one location, so we're going to be on guard for that. All right? So, except in this case, it gives us a particular t, so we don't have to worry about it as much. So, now, again, I got to write the equation of a line. It's not a slope of a line. So, I need a coordinate. Again, t is equal to 3 pi over 4. We know x is equal to 4 cosine of t. So 4, I'm going to do x of 3 pi over 4. 4 cosine 3 pi over 4. Y is equal to 3 sine of t. And I'm going to find y of 3 pi over 4. So 3 sine 3 pi over 4. All right, we've already found these trig ratios, so it's just a matter of popping it in. So we have the coefficient of 4. We knew that cosine of 3 pi over 4 was negative root 2 over 2. We know the coefficient is 3 for the other one, and the sine has a ratio of radical 2 over 2. So one of them we could simplify a little bit, the other we're stuck with. Either way, at least we're going to get relatively clean values. So negative 2 root 2. And the other one is what it is. I'm just going to make it look a little nicer. 3 root 2 over 2. All right. So now I have a slope and I have a point. The coordinates, the x and y values, make up my point. So I have a point and a slope. That's suggesting that we should use the point slope form for a linear function. So y equals m times x minus x sub 1 plus y sub 1. All right, that's the way I write it. You may have learned it as y minus y1 on the left-hand side, but I never saw the point in that, so I just add the y1 to the other side. So y equals 3/4 x minus a negative, so x plus 2 root 2 plus 3 radical 2 over 2. This is one of those weird situations where the original function would be nice and easy to graph if you put your calculator in parametric mode, but then you'd be questioning, okay, so what do I do with this? How do I graph that in order to verify my work? I could actually show you that really quickly, because the alternative to that is to solve, to convert this over to rectangular form, solve for y in terms of x, put that in your calculator, but then it defeats the whole purpose of doing all this stuff. All right?
I know you went through the derivative first and then you did the substitution. Why couldn't we have just used tan theta straight away? And then just substituted, you'd have got the slope, just all direct, plugins for the x and y. Could you have done it that way?
Cotangent?
No.
Because cosine over sine?
If you did tan theta is equal to y over x, right?
Tan theta is equal to y over x, yeah.
So we get, if you just substitute, the values for t as 3 pi over 4, which would solve, you would get the value for x directly, right?
That would give you a -1. So I don't think that would cut it.
No?
Nah. Because that would give you the tangent ratio, but not necessarily the tangent line. Because it gives it over an interval, not instantaneously. That's, I think, where the issue would be.
I just substituted value 3 pi for t, and I found the value of the exact whole circle.
Are you talking about the original function?
Yes.
Okay, so you did the ratio of y over x, and that gave you the 3/4. So if you take the derivative of that, y dx 3/4 tangent theta. I think you're introducing a rate, like the theta dt in there, if you do it that way, yeah. But it works out to give you the 3/4, right? So you feel good about it. You're like, why do all this work?
That's what I was wondering about. Just
Yeah, I think it might be a lucky circumstance. All right, so let me show you on the calculator how to check this real quick without getting into rectangular stuff, because that would just kind of defeat the purpose. Please let it work. Computer 1 is what it should be. It's like when I plug that in, that doesn't want to work, and then, okay, so this is where I was last class, right? This is the same problem I had. That I know works. Well, let me just make sure this is going to work. Alright, input, video. Turn it on, get rid of the glare. Let me resize it this time before I run into the same problem I had at the beginning of class. Okay. Alright, well, we'll see. Hopefully it'll all come out in the videos. But what I want to do is, again, put my calculator in parametric mode. So if you didn't have your calculator the first time I started talking about that, or a second time, what class is this? Second, third? It's not the second, is it? No, okay, that's all that really matters, I guess. So I'm right in saying that I probably talked about it maybe more than once, I don't know. But we'll see. So you want to go into the mode menu. Fingernails are clean, so I think we're good. All right. And then convert it over to parametric if you haven't already done so. Right, hit enter on that. Right, so that is that option right there. Right, regardless of which calculator version you have, there is a parametric mode. It just might say par on one of the older ones. Right, so now when you go into y equals, it asks you for x of t and y of t. Right, which is good. So let me get rid of this stuff. Calc 2 stuff there. And then what I'm going to do is I'm going to put in the original functions. Was it 3 cosine t? So I'm going to type in 3 cosine of t. Now, again, just in case you either weren't here or you missed it the first time, that key xt theta n, that changes depending on the mode you're in. We were in function mode, so it would bring up an x. Now we're in parametric, so it's going to bring up a t, which is what we want. So just bring this back. 3 cosine t. Close it up, hit enter. All right, and then 4 sine t. Same approach. All right, so then we get to the equation that we just came up with, our tangent line equation. Now, that's a y equation. When I told you last class how to convert from function mode to parametric mode, it really just boiled down to how you define your parameter t. So what we're going to do, unless you're told otherwise, is we're going to let x equal t. And then we're going to type in our y equation just how we have it written down on paper. It was 3/4. I'm going to use the alpha y equals approach to create a fraction, just because I like the fractions look nicer that way. So alpha y equals the first option, so 3/4. And then right arrow to get out of that fraction tool. All right. Then open paren t instead of x plus 2 times the square root of 2 and then plus the 3 radical 2/2. So plus, I'll use alpha, again, alpha followed by y equals to bring up the fraction tool. 3 times the square root of 2/2. Right? The idea here is I'm letting x be equal to t. So if I were to just imagine I needed to convert this back, I would do it by substituting. Substitution. And so since I'm defining x as being equal to t, I could then replace the t in this equation with an x and have exactly what I started with. Right? So you can always convert a function into parametric form just by defining x as the parameter t. But if it's moving at a different rate, maybe one function is moving at twice the rate of another, then maybe you let it be 1/2 t or 1/8 t or maybe 10 t. You know, you can vary the parameter itself. But this will get the job done. And so now when I graph it, x2, y2 is going to produce that tangent line. All right. So the reality is you could have always been working in parametric mode, even for ordinary functions. So if I wanted to graph just a simple sine wave, let the x equal t and y equals the sine of t. All right, and that would be it. All right, question?
Yeah. How do you use the fraction?
Hit alpha and then y equals. So that green alpha key, and then the y equals, and then it's the n over d1.
Okay. Cool.
And there's other ways to, I mean, you could just use regular division, but I find that I experience less stress when I use the fraction key because now I'm not worried about order of operations. Right? It's just a nice little feature. So I'm going to graph this. I have no reason to think it would be a funky domain or range, so I'm just going to do a standard zoom 6. So there's my ellipse. and there's my line, but it's not really a line, right? It's kind of a line, it's part of a line. A little line set, maybe an array. Well, it would be an array if it went off the grid. So it's a little line segment. Remember, your parametric equations are defined based off of what you let your t parameter min and max out to. All right, so this is saying only go from 0 to 6.28 seconds. I can change that to whatever I want, negative 10 to 10. So I'm going to change my window, my T min and T max, to something a little bit more extreme. So negative 10 to 10. T step, remember we want to keep that small. In a case of a line segment, we're not worried because if it's going to connect 2 points along the line segment, it's going to come up with a line segment, so that's fine. It's when you have curves, that's where you have a problem. So I hit graph, I got my ellipse. Now there's a little bit of a pause there before it starts creating the full-blown graph. Now, what it's doing is it's graphing this for from negative 10 to 10 in terms of seconds. So it's tracing around this ellipse probably a couple times before it starts tracing the curve, the line itself. So one setting that I recommend, if you go into your mode menu, and again, all the calculators have this setting. You have a choice between sequential and simultaneous. Put it on simultaneous because if you have multiple equations in your y equals at any one point, it'll graph them at the same time instead of waiting for one to finish before it starts the next one. So then you try it again, and you can see that it's working on them both simultaneously. All right. And there you have it. I mean, it looks tangential there. I mean, it's a little iffy. Maybe it intersects, but I mean, we're confident in the math, I think.
I think you put the parametrics in wrong, with the wrong coefficients on each one. Because I think it's 4 cosine, 3 sine.
Indeed. Cool, now I don't have to fake an explanation for why the graph didn't look perfect. Ah, look at that. That's the way you draw it up in the playbook. My brain accepted that ellipse as correct because that was the ellipse that we drew on the previous page, or 2 pages ago, and it was like, well, it must be right. Because that's what we did before, but it was a completely different question, so it wasn't. Ah, I was like, where did it go? Yeah, sure. Wait, you're whoa. Oh, pentagons? Oh, okay, that's easy. All right, so hit window and make. Oh, you know what? Hit mode. Oh, you're good there. Okay, so you're in radian mode, but your window is talking in terms of degrees. So make that negative 10 to 10 and make your t step like 0.1. Yeah, it should be pretty small there, graph. Yeah, no, it's looking pretty smooth. Yeah, no problem. Because of in your window, you want that to go to something negative, so like negative 10.
Oh.
And that'll get the job done with the graph. No problem. You know, one thing that I'm very guilty of that, you know, like I hesitate to admit to it because this shouldn't be something that I still do. Now, if you do it, it's fine because, you know, like you have been doing this for 20 plus years. Sometimes I'll change the window and then hit zoom 6 again and be shocked that I didn't get the graph I was looking for because zoom 6 puts it back to a standard view. I will have manipulated the window and then out of muscle memory I'll be like zoom 6 instead of hitting graph, and all of a sudden it resets right back to where I started. It's like, what went wrong here? Like that's classic me though. Okay, find all points of horizontal and vertical tangency given the parametric equations. Now, if you're doing this on your own, test, quiz, whatever, I recommend you take a look at the picture first and see what's going on. But we're not going to do that now together anyway. I'll do it later. We're just going to dive into the calculus of it. But if you want to pop it in and take a look, I'm not going to begrudge you that. But horizontal and vertical tangency. Horizontal tangent, I'm going to abbreviate HT. Slope of tangent is equal to 0. Vertical tangent, slope of tangent undefined, so I'll say is equal to 1 over 0. All right, there's more to it than that. What's that? Because undefined could always be simplified down to 1 over 0. Because if I had like 10 over 0, I could divide top and bottom by 10, and it would simplify to 1 over 0. So it's a nice nifty way of writing it. All right, but I'm trying to get across the reciprocal nature of 0 and undefined. All right. So the issue is that there's a little bit more to it than that because you have limits involved. The limit as you approach the point of tangency from the left and from the right should be approaching the same kind of infinity if you're looking at a vertical tangent. Opposite infinities if you're looking for a cusp or something like that. But we can work around that. Like the limit rules that bedeviled you back in the day, I don't think you're going to find too much trouble with that, at least until we explore. And I don't want to scare anybody. Like we're going to focus on limits when we get to multivariable parts, the parts of this course. But even then, it won't be that bad. So what I'm going to say is we're going to get into the calculus of it and then compare what we get analytically with what we see in the graph and then see what's up. All right. Bottom line, long story short, we got to take the derivative again. So dy dt, dx dt. dy dt is going to be 2t minus 3. dx dt, 2t plus a 1. Now we could, with this, make a dy dx, which is the quotient of these two, 2t minus 3 over 2t plus 1. But then I go back to what I started with here, and that the horizontal tangent is when the slope of the tangent line is equal to 0. Right? So if I were to set this derivative equal to 0, that would be essentially the same thing as just setting dy dt equal to 0. All right? And if I were to look for the vertical tangent, I would be setting the derivative equal to 1 over 0. That would be the same as just setting the denominator equal to 0. I'm actually going to do the work and show you how that's the case. And then after this problem, you can kind of just streamline it for yourself. But for a vertical tangent, I'm going to go red for those keeping score at home. Oh, I should go, I wrote horizontal tangent first. I'll write that first. We'd be looking at 2t minus 3 over 2t plus 1. We'd set that equal to 0. That 0 is over an understood 1 if we're making a proportion out of this. Cross multiply. We'd be looking at 2t minus 3 equals 0. All right, so this is the same as setting dy dt equal to 0. That was the most productive one, but also the most painful one. And also, when I say it like that, the most disgusting one. Apologies. For the vertical tangent, 2t minus 3 over 2t plus 1. I'm going to set that equal to 1 over 0. Again, cross multiply. And we'll be looking at 2t plus 1 equals 0. And again, same idea. So you get a little bit of a shortcut out of this. And that shortcut is basically telling us that I never really had to put it together in a dy dx to begin with if I'm looking for horizontal and vertical tangents. Okay? So if I just take my dy dt instead of equal to 0 and solve, that'll get me on the way toward finding my horizontal tangent. And the same idea for the vertical tangent, just set the dx dt equals 0. All right, so we're looking at t equals 3 over 2. T equals negative 1/2. All right. So directions, always important, those pesky directions. But find all points of horizontal and vertical tangency. Points. Points are locations, not moments in time. All right. So we have moments in time. I need to know what locations those correspond to. That's where the calculator comes into play. All right. So I'm going to type these in first before I put it on the video. Let it focus. This is brutal. I'm sorry. It's like I thought it would be better by now, but it's not. I don't know. I think it might be something to do with like walking in from 85-degree weather into like blasting cold air conditioning, like slamming you in the face. So.
You sleep the AC on?
What's that?
Sleep the AC on?
Normally I do, but recently I haven't. But the damage. Oh yeah, please. No, thank you.
Oh, sorry.
But
I like cold in the summer doing that.
Yeah.
AC on.
The summer cold is brutal. And you know what? Like that might have been what happened because it just came on in the last couple of days. But that doesn't mean the damage wasn't done before I started turning the AC off. So, thank you, appreciate it. So, we have our equations in, and for some reason, like auto adjust going nuts here, but I think we can make it work. So, I'm gonna graph it. I'll just do a zoom 6 and see what the picture looks like. All right, now we run into it's not a problem, it's just the question or concern of, does it go further in the opposite direction? All right, so what I do is I expand my t information here to account for that. All right. Always taking care to include the appropriate domain if it's stated, but in this case it's not. So I'm going to go -10 to 10, and I'm going to hit graph. It looks like I have more stuff going on here, but I have the important stuff, and that's really all that matters, because I can see a clear vertical tangent here, right? It goes vertical, right? And I can see a clear horizontal tangent there where it goes horizontal, right? So I just need the points. I can do that. Second trace. Second trace is the name of the game if you're ever looking for coordinates. So I'm going to type in, I'm going to hit value, and then I'm going to type in 3 over 2. All right, so this will give me, we were looking for horizontal tangents. So this should coincide, when I hit enter, it should coincide with something in this neighborhood. All right. And it does. Not only does it plot it, but it also tells you what the ordered pairs would be. Right? So it's giving me the coordinates of those points. Now, maybe you want the fractional version of those numbers. Little nifty trick. This calculator, it stores values. So when it says x is equal to this and y is equal to that, it means that x, if I were to hit alpha, the store key. So let me just pull this up for you. You see it right there, that little x? If I hit alpha and then the store key, that'll bring up an x. Hit enter, it brings up that number. All right, 3.75 is not a crazy decimal, but now I have the ability to math bracket. I can convert it over to fraction form. So I hit math, and then option 1, and it'll convert it over. Do we need to do that? I don't know. It's nice. It's a nice nifty feature. I don't have to worry about rounding if it's a crazier decimal. Do the same thing with y. Alpha 1 brings up the y. That's the decimal it gave us. So convert that over, math, enter, enter, and you get 11/4. So 15/4 and 11/4. All right. So I'm going to make a note of that. So that's my horizontal tangent. Now I just need my vertical tangent. All right, so I'll do that over here, I guess. So back into the graph, we add -1/2. So second trace value, type in -1/2. -1/2 or -0.5, it doesn't matter. It plotted to the vertical part of the graph. Beautiful. That's what I wanted it to do. For some reason, it won't record unless I hit that little guy. All right, so it plotted to the vertical part of the graph, and it gave us the decimal values, one of which I don't really need to worry about. I know that's -1/4. The other one's 6.75. Maybe I want the calculator to do the work for me. All right, so quit. Second mode. Bring up the y. Hit enter. Math bracket. And I get 27/4. All right, so now I know that my vertical tangent is -1/4 and 27/4. I can tell you that my tests are not designed to be feared. All right, they're designed for you to show your stuff, not to be terrified of the experience. All right, so, but you'll see as we get closer. So hopping up to page 7, we'll tackle number 4 together, and then I'll just preemptively put a star on number 5. Kind of reserving my teacherly right of doing the easier one with you and then leaving the more challenging one for you to try on your own. All right, but it's the same rules as the other starred problems. It's you're going to try it, succeed or fail, and then we'll go over it together anyway. All right, so just bear that in mind. So we're finding the arc length on the interval of 0 to 1. All right. Sometimes helpful to create the graph to get a sense of what you're up against. But when I say create the graph, I mean pop it in your calculator, take a look at the picture. All right? So I'm not talking about a scaled drawing. Regardless of what you do first, ultimately you're going to have to figure out dy dt. It doesn't matter which one you do first, but when I do the derivative process and second derivative, I usually find dy dt, then dx dt, so that I divide them in the proper order, but this isn't that. All right, so dx dt is 2t. dy dt is equal to 12t squared. All right. Now our rule is that the arc length is over the interval of a to b, dx dt squared plus dy dt squared dt. So over the interval of 0 to 1, all right, they gave us the restricted bounds. You got to be careful with circular functions, anything that's a closed loop, because sometimes they don't give you the domain, but you have to know, well, it's a circle, so it's got to be between 0 and 2 pi or 0 and pi, depending on the frequency. All right, so just something to be cautious about. dx dt is 2t, so 2t squared, quantity squared, plus 12t squared squared. dt. On the interval of 0 to 1, we're looking at the square root of 4t squared plus 144 t to the fourth dt. All right, now there's some common factors that can be pulled out. And then you can go that route. In this case, you'd be doing a little trig substitution in order to find the integral. The scheduling process happens so late in the summer, so I normally I can point to like and make comments like, well, you all took me as a teacher for a reason, so here's the reason, you know, but I don't know that that's necessarily the case. So this could be a surprise to many of you. My policy on definite integrals, because I don't like to do a double dip, you've already been assessed on this in Calc 2. My policy on definite integrals is pop it in your calculator and get the answer. All right, it's indefinite integrals where you have to do something else potentially. All right, so and you know, you'll get enough situations where you have to do stuff by hand, you won't have a choice, that I don't worry about like, oh, you didn't do it by hand, that means you don't know math or something. I don't know. Different people have different philosophies, but I find that most of the people who take me as their teacher for this course are doing it because I allow a more liberal use of the calculator, right? So if you didn't know that coming in, surprise. If you did know it coming in, then I just confirmed what you already know. All right, so bottom line is I'm going to kick over to the computer. I'm going to remind you how to find a definite integral on the computer, assuming that it actually wants to function. Oh, that's computer 2. 1, I mean, so it's probably computer 2. Right. This is just just one of those. We do what we can. Math 9, Yeah, you could scroll down, but it's the one that says FN int on your calculator. It won't look like that on the screen, assuming that your screen is set up properly. All right, it should look like just a good-looking blank integral. And then in that blank integral, you just type. All right, so that's what I'm gonna do. 0, hit the up arrow, 1, right arrow, square root. You could use x's, t's, whatever. I'm going to use x's. 4x squared plus 144 x raised to the 4th. Pop an x on the outside. And then hit enter. And you're looking at about 4.149. So approximately 4.149. Say it again?
I did it a different way.
You did it a different way?
Yeah, I put it in to graph, and I put
Y1?
then I put a second trace, and then I find the end where it's like 0 to 1.
Oh. And you got the same answer?
Yeah, look, I'll show you.
Oh, because you did second trace, option 6.
Option 7.
Oh, 7, yeah, because 6 is derivative, yeah. Yeah, that works.
Where'd you go with that again?
Math, option 9.
Okay. Thank you.
No problem. Oh, this doesn't lock in place. That's unfortunate. All right, but let me just show you really quickly. A shortcut key, alpha window. The newer calculators have more stuff, but the older calculators have the first 5 options. This is like the most commonly used, but not the easiest to find set of functions. So odds are, if you're looking for some weird function in your calculator, it's in this menu, and that's alpha window that brings that up. All right, so in that case, you just choose option 4 and you're good to go. All right, so it's a little quicker and easier that way. So kill that, kill that. You'd be looking at the square root. It would become 2t, and then 1 plus 36 t squared.
Okay.
dt, and then you'd let u be equal to 1 plus 36 t squared. And then you'd be looking at, when you take the derivative of this, du is equal to 72 t dt, with the idea being that we want to get rid of these guys. So I have 72 t dt. I want a 2 dt, 2t dt. So I'm going to divide both sides by 36. So 1 over 36 du would be equal to 2t dt.
Okay.
So then that would allow this substitution to happen. So I'm going to replace the 2t dt with that. So it's going to become 1 over 36. The square root, instead of 1 plus 36t squared, that's going to get replaced with a u. And then we'll have a du going from 0 to 1. Well, actually, it wouldn't be 0 to 1 anymore, so we'll just leave it without bounds. So then it becomes 1 over 36 u to the 1/2 du. Increase the exponent by 1 becomes 3/2. Divide by the new exponent, so it's the same as multiplying this by 2/3. So we're talking 1 over 54, if I'm not mistaken. Oh wait, we're multiplying it by 2/3. So 1 over 18, just make sure. Yeah, 1 over 54. All right. And so that's the same as 1 over 54 times 1 plus 36 t squared to the 3/2. And then you would evaluate that over 0 to 1.
Okay, that's going. This is going.
Right. So if I put the 1, let's see, the 1 makes it clean. Yeah, so 1 over 54 times, I'll just write it, yeah, 2 to the 3 halves minus 1 over 54 times 1 to the 3 halves, so just that. Yeah, I don't think it would clean up any more than that without putting a decimal point.
Am I registered now?
What's your last name again?
Menezes?
Yes.
Oh.
You're definitely on there.
Thank you very much.
No problem. All right, find the arc length if x equals t sine t and y equals t cosine t with t between 0 and 1. All right, so we're still going to need derivatives, and we're still going to need antiderivatives of those derivatives. So it's just one of those where we got to kind of grin and bear it and just get the work done. So dx dt, I'm sorry, dy dt I usually like to do first, because it's all got to go in that integral formula. All right, so it's a product of two functions, t and cosine t. So product rule comes into play. First times the derivative of the second, so negative sine t, plus the second, which is cosine t, times the derivative of the first, which is just a 1, so I don't have to write anything more than that. I can clean it up a little bit, making it negative t sine t plus cosine t. dx dt, same idea. Product of two functions. So the first function times the derivative of the second plus the second function, which is just a sine function, times the derivative of the first. And again, cleans up just a smidge. I mean, really it just cleans up to remove the dot that I wrote in, so undo. So it's the definition of a smidge. So this should be fun. What I need to do is set up my integral. We derived the formula last class. It's dx dt squared, so this whole shebang squared, under a radical, it's like jutting up against that integral symbol from another problem.
Although you did dy dt first, the order is dx squared, and then it's
Yeah,
okay.
I did it first because
Just
I
to keep it simple.
yeah, and I get in the habit when I have to take a derivative, I just want to have it in that order. So just kind of cleaning that up. Let me draw a little line of demarcation here. All right, so dt on the interval of 0 to 1. So, question would be, what do we do with this? And the answer would be, plug that bad boy right in your calculator and call it a day.
Really?
Yeah, I'm not doing this by hand. You kidding me? What do you think this is?
What did you expand it?
You could expand it if you want, but there's plenty of instances where I'm going to make you do stuff by hand, and I'm sure you're thoroughly going to enjoy it. This is a Calc 2 problem. I'm not doing that. This is Calc 3. We earned our place here. We went through those trials and tribulations. The torture. I don't know. Maybe it was great. I enjoyed my time in Calc 2. Now, the one concern, though, and it's a legitimate concern, is what if I type it in wrong? Well, then you're going to get it wrong. So don't type it in wrong. Okay? It's a double, triple, quadruple check. Because there's no work for me to evaluate.
The ball is still having
What's that?
calculator.
Yeah. So open paren, t cosine, t, close them up, plus sine t. Close it up for sine and then square it. Now I'm just gonna carefully double check this and make sure I didn't botch it. I think it's fine. So I didn't really carefully double check it. I'm just saying that I'm doing that. T, sine, t, close it up for sine, plus cosine t, close it up twice, square it, and put a little t in this bad boy out there. And then scroll back and start from the beginning and make sure. The transition from screen to screen is a little annoying though, because it kind of jumps a little bit, so it's easy to lose your place. But take a quick look and make sure everything's the way you want it to be. Specifically, every set of parentheses you open should have a corresponding set of parentheses to close. All right. The mode should be radian. Double check that. Good to go. Moment of truth. Nice. Nice. All right, so we're looking at approximately 1.148. Now, don't get me wrong, this problem is reasonably fun to do by hand. Distributing things out, and bringing all your Calc 2 knowledge to bear, but that's not the focus of the course. We need to get to the focus of the course so we don't get bogged down with that kind of stuff. Or at least in this class. I mean, I don't know how many people have experience with Calc 3 in other capacity. I looked through the surveys, but I didn't really like study them. I really just looked to see where you wanted to go, if you could go anywhere on the earth, because of vacation ideas. But so far, pretty standard stuff. There were a couple gems in there. A lot of people want to go to Australia.
Really?
Yeah, I think I'm gonna need to check that out at some point.
What about Albania?
Albania, yeah, I'll put it on the list.
They have a lot of beaches over there that not a lot of people have.
Oh, really?
Yeah.
All right. One of my
Also, we go scuba diving there because it used to be a communist country. So when it opened up, not a lot of people know about the coral reefs over there. So it's really cool to see.
Oh, that's awesome. Yeah, I have one of my cousins is married to an Albanian girl, and they're always saying, "Oh, we should all go. We'll take a big family trip." So, yeah,
Albania or Kosovo?
What's that?
Albania or Kosovo?
She said Albania. So.
Because it's Kosovo, Albania, and then Albania.
So I should call her on that and say,
Yeah.
all right, I'll do that.
We did the same thing. It was like,
Yeah, but like it puts me like in the know.
Yeah.
Yeah, and that.
Oh, how do you know that?
Yeah. It'd be like a big. Yeah. All right, polar coordinates. Now that we know everything there is to know about parametrics, that's not really the case. What we have to do is start learning about polar coordinates so that we can start merging the two ideas. All right, because in polar coordinates, you start getting into just circular reasoning, but you could also merge the ideas that come from polar coordinates with our understandings associated with parametrics, and then you get the idea or the reasoning that comes into play when you say, okay, well, what if I introduce a time element to something that's in the polar coordinate system? Okay, so we're taking a time element and putting it into the function coordinate system, the rectangular coordinate system on the previous pages. Now we're going to learn about the polar coordinate system, and then we're going to introduce a time element to that. All right, so very interesting stuff coming your way. But this very, very popular pre-calc topic, recurring theme, that may or may not have been taught, needs to get addressed. All right. So I talk about the structure of a polar coordinate system. Fixed point O is called the pole or the origin. Most people go with the origin because they're familiar with that. Say, well, in the XY coordinate system, it's called the origin. So I'll just call it the origin for everything else. That's fine. But then, if you think of the polar coordinate graph as a top view, for example, of the planet Earth, and every ring represents latitudes and every line represents longitudes extending out from that north pole, then all of a sudden you kind of sort of want to call it a pole because it would make sense, physically speaking, to call it that. Polar axis, if you were to overlay the polar coordinate system on the rectangular coordinate system, the polar axis would correspond to the x-axis. All right, horizontal ray directed towards the right, it's in the direction of 0. All right. In order for the polar coordinate system mathematically to jive with the xy coordinate system, we need to have 0 degrees going to the right, even though physically speaking that doesn't make sense. All right. In the real world, 0 is not to the right.
It's not right.
Yeah. Point P can be defined by the coordinates r comma theta. R represents the radius, theta represents the angle of movement. All right, so everything's in terms of a movement, and the idea is that you're pulling away from the pole in some capacity. Those two dimensions, in this case, would be a counterclockwise or clockwise movement, and also a distance traveled from that pole. All right, so if you know those two parameters, really, then you know the location of a point in the polar coordinate system. All right, and that's all addressed here. So these are our little cliff notes, I guess, if you will, for that that concept. If r is positive, then you're moving toward a given angle. All right, so if I have something like 3, 30 degrees, the r value is positive. That's telling me I'm taking 3 steps toward 30 degrees. I'll go through some examples in a second, but that's just the gist of it. If theta is positive, just like in the unit circle, and in fact, I would say if you have a decent understanding of the unit circle, you're not overly concerned with the theta values, because theta behaves like theta has always behaved. Positive theta is a counterclockwise movement around the unit circle, and if theta is negative, it's a clockwise movement. All right, so go the other way. This is like the polar graph. It's like the unit circle on steroids. All right, the inner ring, that is the unit circle. All right, that's the one with a radius of 1. Then you have a radius of 2, 3, 4, 5, and so on, out to infinity. So if you know everything about the unit circle, so coordinates, radians, degrees, then you really know everything about a polar graph, except you're allowing for the radius to be more than 1 or less than 1. All right. If r is negative, you're just taking r steps away from the given angle. So my example before was 3, 30 degrees. I think. So 3 steps toward 30 degrees. So here's 30 degrees, that would just be, I start at the pole, I'd be like, boop, 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 right there. That's 3 comma 30. Negative 3 comma 30, I'm at the pole. I'm gonna aim for 30, but I'm gonna take 3 steps in the opposite direction. Boop, 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 right there. All right? So 3 steps in the opposite direction for 30. All right, like I said, we'll do some examples in a sec, but that's just the overall gist of it. Ah, man, my example on the fly was almost exactly the example that's here. That's unfortunate. I don't like when that happens. And we'll also learn how to convert back and forth between rectangular and polar coordinate system. So, this first one, right, yeah, is telling us to take 3 steps toward 60 degrees. So you identify 60 degrees, you're taking, let me make my marker a little thicker. 1, 2, 3 steps in the direction of 60 degrees. Make it even, I'll make it obnoxiously big. There we go. Alright, so that's point P. 3 steps in the direction of 60 degrees. Second one is telling us to take 1 step away from, which is not spelled the way I was about to spell it, 7 pi over 6. So your default is that you're standing at the pole, right? Standing at the pole, looking at 7 pi over 6, I'm going to take 1 step in the opposite direction. Sometimes a ruler can be helpful. I don't have one, so I'm going to use this. So, yeah. So just trace the line in the opposite direction so you know what path you're going on. That being said, if you just look at the scale around the graph, I kind of go a little bit rogue when it comes to this. I give you these numbers around the circle. Most polar graphs don't come with the numbers around them. I just figure, I mean, you've been tested on that too. You know, like you've been tested on derivatives, antiderivatives, things like that. At some point, it's like, is the last math class you take going to be a test on every single math class that came before it? I hope not. But it's possible that that's the case. I just don't want this to be my experience for you. All right? So I'm going to give you these values so that if you're aiming away from 7 pi over 6, just aim for the radian measure that also has a denominator of 6. Same denominator in the opposite direction is going to be the direction you're going to want to go in. All right, so 1 step in the opposite direction from 7 pi over 6. And you know, for the record, I don't intend this to be a semester where I'm just telling you repeatedly how wonderful I am. It's really just because in the past, folks have expressed concern with, well, you're doing all this stuff on the calculator. What if I need to do it by hand? Like, and it's a legitimate concern. So going into the next course that you take after this, what if they say, well, you need to do all that stuff by hand. What's wrong with you? The stuff that I'm allowing you to do on the calculator is not stuff that's unique to this course. Right? You've already been assessed on doing that stuff by hand. Right? That was Calc 2 or classes prior to that. Right? There will be stuff that you're going to have to do in this course by hand, and that no calculator is going to save you from that because it's just they're not designed to. Right? So to allay any concerns that might be there, I figured I'd address it. I have this tendency to over-explain things, and so that might be the case, but I'd rather do that than not. Negative 2 pi over 3, if you make use of the scale that's there, here's 2 pi over 3. That's this much in the counterclockwise direction. if you want to count little line segments here, you go 1, 2, 3, 4, 5, 6, 7, 8 of them. I just want to do that going the other way. 1, 2, 3, 4, 5, 6, 7, 8. That's going to put me at 4 pi over 3. So this one's going to be 2 steps in the direction of 4 pi over 3. Now a little nifty shortcut, if I'm looking for a negative angle, find the positive angle and reflect over the x-axis, or the would-be x-axis, because it's not technically the x-axis. So if I needed to find, let's say, negative 3 pi over 4, I find positive 3 pi over 4 and reflect over the x-axis, and that'll get me to the equivalent of negative 3 pi over 4. And there's other ways to do it, but that's the quick visual way of getting it. All right, so again, just to recap, this one is saying 2 steps toward 4 pi over 3. And you know, nifty shortcuts aside, worst case scenario, you know how many radians there are in one full turn of a circle, right? How many are there? There's 360 degrees. How many radians does that correspond to? 2 pi. All right, so if you're going 2 pi in total and you want to figure out, you know, what negative 2 pi over 3 is, you could always use addition and subtraction to figure out the missing angle. So all you would do is just subtract 2 pi over 3 from 2 pi, and that would give you the 4 pi. All right, so doable any which way. Now this one is the double negative situation. So we're going in a counterclockwise direction 135 degrees with my nifty shortcut. It's telling me that I'm really looking at 225. So reflect the 135 over the axis and you have it. But I'm going to take 2 steps away from 225. I used red, blue, black. I guess it's black. 2 steps away from 225 degrees. That would be 2 steps toward 45. I'm going to chuck a little S in there. Alright, so pretty weird. You know, definitely not quite as simple as plotting x comma y. Over 2, up 5. Plot a point, call it a day. Here, there's a little bit more thinking involved. And so when you get to cases where you have to actually graph a function, you're like, wow, this can get out of hand pretty quickly. But again, I'm the calculator guy, remember? So everything will be fine. But before we get too hot and heavy into creating functions, let's talk about how we can convert back and forth between polar and rectangular coordinates. Very, very important, because yes, polar coordinates in and of itself are wonderful. Rectangular coordinates, we know what those are all about. Bridging the gap between the two is what we're going to try to do here. And this is a little twist off of what we were talking about last class when we were getting into unit circle calculations. Any point in polar space can be defined based on, again, theta and r, so distance away from the pole and the angle from the polar axis. But we could also decompose it into a right triangle x and y, with legs x and y, I mean to say. Exactamundo, right? But I'm going to take a sec and show the step that comes right before that, and that is, if I'm looking at theta, I could say that the cosine of theta is equal to the adjacent over hypotenuse x over r, and that gives us x equals r cosine theta. All right, because a consequence of that relationship, this one trig ratio actually tells us more than one thing. It gives us more than one conversion. So if I were to take the inverse cosine of that, I would then determine that theta is equal to the inverse cosine of x over r. So I now have a way of converting r's and thetas into x form, but if I have an r and an x, I can convert it to give me the value of theta. I can do the same thing with sine. Sine of theta is y over r. And as you said, y equals r times the sine of theta. But also, theta would be equal to the inverse sine of y over r. And while we're here, might as well throw a tangent in there. Tangent theta is equal to y over x, opposite over adjacent. Now I could solve that for x or y. It's not really going to advance the plot. The only meaningful one that it's going to give me is that inverse tangent of y over x is equal to theta, or theta is equal to the inverse tangent of y over x. So that allows me, if I'm given values strictly in terms of y and x, to come up with a theta related to that. And, you know, I don't want to be neglectful. There's also the good old Pythagorean theorem. One little triangle is given all this. It's crazy. X squared plus y squared equals r squared. Take the square root, and you get r equals the square root of x squared plus y squared. Technically plus or minus, but as it's going to turn out, we're not overly concerned with negative r values when it comes to functions, so I'll show you what that means in a little bit. Algebraically, it comes out in the wash. Alright, but now we have the means by which we can convert from one form to another. You just gotta kind of cherry pick which ones are the most useful formulas. Alright? So we'll just kind of decide based on what we see. Find the exact rectangular coordinates of each point. So if we're looking for rectangular, what we're given is polar. Based on the form, it kind of makes sense because they have a degree measure in there. So I have an r and a theta. I need an x and a y. I have an equation where x is all alone on one side. X is equal to r cosine of theta. And I have one for y also. Y is equal to r sine of theta. So my r value is 3. Cosine of 270. And then 3 sine of 270. Oh, what is that? How does that work? Did I just take a screenshot accidentally? Alright, well, whatever. So what's the cosine of 270? 0. So 0 times 3 is going to be 0. What about the sine of 270? -1. So 3 times -1 is going to be a -3. So now I have my coordinate 0, -3. The axis values on the polar graph correspond with the axis values on the rectangular graphs. So if I'm telling you that this is 3 steps in the direction of 270, that's 3 steps directly downward, which when you plot 0, -3 on XY axis, that coincides, it should make sense. All right. So that's how you go the one way. Let me show you how to go the other way. So I'll put a star on the second problem. Well, second problems. Because in the case of number 3, we're given x and y. And I want to come up with r's and thetas. Well, just looking at all of my information above, I can see that I have a formula that solves for r in terms of x and y right here. And I have a formula that solves for theta in terms of x and y right there. So I'm gonna snag those two bad boys and bring them down into the party. All right, so r is equal to the square root of x squared plus y squared. Theta is the inverse tangent of y over x. All right, so zero squared plus -49 squared. That's going to give me a 7. And then for the other one, oh, sorry. It would have been 49.
Yeah.
It's one of those where I put the answer in the question. Whoop. Which is 7. Thank you. Inverse tangent, -7 over 0. All right, so I got the r value. The theta value is a little trickier numerically, but if you consider the nature of the problem, you probably already have it. So tangent here is undefined. So you'd be asking yourself, where on the unit circle is the tangent undefined? Happens in 2 places. And this question's calling for degree answers. Right? So just going around the unit circle, where would you expect tangent to be undefined?
2.
Pi over 2 and -pi over 2. So we would say 90, to keep it in this domain, 90 and 270. All right, because they're calling for a 0 to 360. All right, so if I were to plot this set of coordinates with 0, -7, so if I were to plot that on the rectangular coordinate system, 1, 2, 3, 4, 5, 6, 7, it would be somewhere around here, 0, -7. I couldn't find a graph grid that was big enough that looked this cool. Yeah, it's going to be 270. Exactly.
The graph didn't even come out on the paper.
Oh, it didn't even come out on the paper at all? Oh, that's
Not the circle.
oh, that's the best part. You see what I'm going for though, right? I mean, it's glorious. You look at it, you're like, oh, that's how it all works. Like, you see the rings coincide with the rectangular coordinate system, but only on the axes. It's beautiful, but it's not on your paper, so that sucks. All right, well, note to self, I guess. All right, yeah, but 270 is the winner, because if I'm traveling around this circle, to get to that location, I'd have to go all the way around. All right, So I'm looking at 7. My final answer would be 7, comma 270 degrees. Normally I'd say yes, but because this problem gave particular constraints, we'd be stuck. Such a nice looking guy. Probably going to be required calculator. So here we're saying that the radius is 3 regardless of what theta is. All right, so if theta is 0 degrees, it's still going to be an R value of 3. If theta is 30 degrees, it's still going to be an R value of 3. If it's 90 degrees, and so on, all the way around. The bottom line is what you're going to end up with is a circle. Undo. What you're going to end up with is a circle. That was good, but now it's filled in. Address the opacity here. None. What you're going to end up with is a circle. Yeah. And that's really all there is to it, because you can go 3 units in any which direction, it's still going to put you somewhere on that path. Alright? If you had an R value of -3, that would mean no matter what angle I was looking at, I was taking 3 steps in the opposite direction. Bottom line, still going to be a circle. So, if R is equal to 3 or -3, it's going to be the same path. Same path as R equals -3. Now this one is saying theta is equal to 3 pi over 4. Implied that that's for all values of R. So for all R. So no matter what my R value is, my theta is always going to be 3 pi over 4. So R could be 1, it could be 2, it could be 3, 4, 5, it could be -1, it could be -2, -3, -4, -5, -infinity. Now this is circular, but this is theoretically it's in 2 dimensions, so it would be infinite. But when we span this out to 3 dimensions, there's my line. When we span this out to 3 dimensions, you're going to see that this really ends up being, every one of these lines that look like lines here will end up being circles, right? Because, you know, if you're close enough to a top view of the planet Earth, it's all going to look flat, right? And if those longitudes were actually traced out on the surface, they would look like lines. But then as you pull back, it looks more spherical, and those lines you see are really just straight circles, right? And so that's what's happening here. We're just looking, and 2 space is really just a microcosm of 3 space, right? So if you're just looking at 2 space being defined as an infinitesimal size little segment on the surface of 3 space, then you have a true understanding of what 2 dimensions are. Really, it's just like the whole, like the ant's perspective. If an ant was on your arm, a person standing on a planet, that kind of thing, size relationships. Right. Now, your calculator understands polar graphs.
I'm sorry, but if you graph the line for negative 3 pi over 4 would be from x.
If it were negative 3 pi over 4, it would be what?
It would be just the opposite of x.
Yeah, exactly. Exact and window. Your calculator understands polar coordinates also. So let me take a second and share that with you. With my clunky calculator interface. Oh, my face. Hello. Now everybody knows what I look like. All right, the likes are going to come pouring in now. I could have lived every day of my life without that happening. We'll see. If you go to mode, again, you have function, we were in parametric, you can go to polar. Hit enter on polar. Now go back into y equals. It's not y equals anymore, it's r equals. All right. Move that over a smidge. All right, the first graph that we were looking at was r equals 3. That's something the calculator can understand. Theta equals 3 pi over 4, you're on your own. Calculator can't handle that one. All right. So, r equals 3. Start with a zoom 6, zoom standard. Now, it should, in theory, look like a circle, but just based off of the rectangular pixels and everything, it always ends up looking elliptical. But if you count tick marks, you can see it's 3 in each direction, so it's supposed to be circular. But the scaling is a little off. You see it's more compressed along the y-axis. Right, so you can play around with it to make it look a little bit more circular in terms of the dimensions of your window, but I don't think that's necessarily worthwhile.
You could use zoom 5. And it makes
The zoom box?
Yeah.
Oh, zoom square, yeah. Yeah, there you go. Very good. That was literally the first time I ever used that one. I've never used zoom square before. Looks much nicer. What did it make the window? Yeah. Because that's precisely what we would have considered. In order to make a square window, it needs to go from about negative 16 to 16 on the x-axis. It's like, well, why'd you do that? It doesn't make sense. So, but it looks nicer, and oftentimes that's all we need. Now, in terms of the window, because the window is always going to be important. Data step behaves a lot like t-step in parametric mode, in that if you make it too big, it starts cutting corners in how it graphs. So if I make this theta step, let's say I make it, instead of 0.13, I make it like 0.3. It's a little bit, well, it cut it short, but it's supposed to be a little bit boxier. Let me make it look obnoxiously larger. I'll make it like 1. All right. So every 1 radian is plotting a point and then connecting with a straight line segment. It only simulates smoothness because when you plot it for a very small theta step, it's plotting every one of those little deviations of theta. So if I say go by 0.01, then every 0.01 of a degree or radian, depending on the mode, it'll plot a point and then connect those, so it simulates the appearance of a curve. Right? So if I make it too large, it's not going to show anything. Right? If I make it too small, it takes forever to graph. All right? It gets there, but it takes a while. Hit on to interrupt if you get into that jam. So, like a 0.1 usually is a pretty good way to go. All right, it's kind of a combination of accuracy and speed, so efficiency by definition. Now, the theta min, theta max is you telling the calculator what theta you want it to start off with and where you want it to end up. Next class, we're going to get into more detail on under what circumstances that's not going to be 0 to 2 pi, because that's what it defaults as. But I'll show you really quickly. If I make this 0 to pi, I only get half of the circle. All right? But depending on the nature of the function, I may not even get that much. Right? If it's some weird trig function, I might not even get half of the overall function. I might only get a quarter of it or something like that. All right? So we'll talk about why that works the way it does and how to navigate that. But for now, I just wanted to go through one more problem, then I'll let you go. And that's related to these bad boys. You're just converting entire equations over from one form into another. The reason I brought up the calculator approach is because it would be really nice to be able to check your work or at least have a sense of what you're aiming for. All right, so for the first one, you just go back to all those formulas that we created on the previous page and just grab one that seems to make sense. So in the case of sine, for example, I want that to go away. I also want the r to go away. But let's just focus on the sine for a second. One of our rules is that y is equal to r sine theta. But by extension, or at least going back in time, that's equivalent to sine of theta is equal to y over r. So I can manipulate this to say r plus 5 times y over r is equal to 0. Our only goal is to get it into rectangular form, so x's and y's. Whether you go the distance and get it into some recognizable standard form is up to you. But once these r's go away, I'm going to be in pretty good shape. The one concern I have is that if I were to do the direct substitution here, I would be putting this radical in 2 separate locations. I feel like that's going to end up being ugly. So I'm going to clear out that r on the bottom by multiplying everything by r. And that's going to make r squared plus 5y equal to 0. And just going back to this formula here, r equals the square root of x squared plus y squared, I can square both sides and make that r squared, bless you, is equal to x squared plus y squared. All right. These are all, I mean, even the ones I'm writing are ones that we wrote on the previous page. It's just, these are the standard formulas that textbooks usually give and things like that. I'm just showing you how you could vary them to make them more suitable for our needs. Because I'd rather put the x squared plus y squared in here once than to put a radical x squared plus y squared in there twice and make a mess of it.
You don't simplify it anymore.
No, you don't have to simplify it anymore. If you were to do that, you would complete the square to make it an equation of a circle, but it's not necessary. Because again, I try to balance like what skills are useful and what like you could benefit from. In this case, I mean, we could spend some time converting it over, but it doesn't really advance the plot. Because in reality, if you were to graph this, the whole point of this lesson is for you to say, you know what? Regardless of how that one shapes up, if I'm putting this in my calculator, that's the one I'm going with. Because I can solve that for r real quick. Just subtract that and type it in, and then I'll have my graph. All right, and so you'll be able to see very easily what kind of graph it is. So I'll put a star on the second one, which in terms of difficulty isn't really much more complicated. I'll tell you, some of these problems become a lot more complicated if I ask you to simplify. So, I mean, there's that, but again, it doesn't really do much for us. The last one, number 9, is going the other way. For this one, we would want to distribute it out. So x squared minus 8x plus 16, and plus the y squared equals 16. I'm going to put a star on this one while I'm here. Now you see the 16s cancel immediately. Boom and boom. I can rewrite as x squared plus y squared minus 8x equals 0. By definition, x squared plus y squared is equal to r squared. And x is equal to x is equal to r cosine theta. The 8 was already there. X is not equal to 8 because that doesn't make any sense. Alright, so this is in polar form. Technically perfectly acceptable in terms of a final answer. But we can go a little bit further. Might as well. I have a common r that can be factored out. And if I set each of those factors equal to 0, I get r equals 0. Now, in function notation, so like a rectangular coordinate system, if x was equal to 0, we'd be talking about a position, right, within the coordinate system. When r is equal to 0, we're talking about a circle with a radius equal to 0. Is anything even there if you have a circle whose radius is 0? Does it even exist?
No.
No. So this is irrelevant. So we're left with the r equals 8 cosine theta equals 0. And then we can solve that for r, and you get r equals 8 cosine theta. So a little bit cleaner of an answer, a little bit more calculator ready. Would you have to do that on a test? No. You stop right here, call it a day. But I just wanted to take a minute to talk about that r equals 0 part of it. Because in the xy coordinate system, if x is equal to 0, y is equal to 0, that's a place. All right? That's a location. It's position 0. But in the polar coordinate system, it's a distance. All right? A circle with a radius of 0 is not a circle at all. It's nothing. All right? So it's not even a geometric figure, so it's irrelevant. So that's where we're going to leave it tonight. If you have any questions, stick around. Otherwise, have a wonderful, wonderful weekend. I'll see you on Monday.